We are beginning a new unit, circles. To start the unit, we'll begin at chapter 10.1, tangents to circles. Please take notes. So we're going to start the unit by going over some vocabulary that you may be already familiar with. Some words should be new, and they might have more in-depth definitions than you have previously learned. So we're going to start with just a circle. A circle is the set of all points that are equidistant from the center. So for example, if this is center P, a circle is the set of all of these points that are all equidistant from P. It's written as circle P, or this little circle with the center, P. Next we have a radius. A radius is the distance from the center to a point on the circle. So from the center P to right here, that's a radius. Or right here, that's another radius. All radii are always congruent. Diameter is the distance across the circle through the center. So this is an example of a diameter. Notice a diameter is equal to 2 radii. There's one radius from the endpoint on the circle to P, that's one radius here, and then there's another radius over here. So the diameter is equal to 2 radii. Or you could say a radius is equal to half the length of the diameter. Next we have a chord. A chord is a segment whose endpoints are points on the circle. Notice a chord stops at these endpoints. So we would name this chord segment AB is a chord. The endpoints are points on the circle. Another chord could be from here to here. That would be CD. Segment CD is a chord. You could have a chord that goes through the center. A chord that goes through the center would just be a diameter. So XY, segment XY is also a chord. It also happens to be, though, a diameter. Here's an example of a segment that is not a chord. If this is your circle, this segment XZ is not a chord because the endpoints are not on the circle. Next we have a secant. A secant is a line that intersects the circle at 2 points. So remember, a line goes on forever, so it does not stop at these two at these 2 points on the circle. So this would be line AB. Line AB is a secant. It intersects the circle twice. Last we have a tangent. A tangent is a line just like a secant. However, it intersects the circle at exactly 1 point, so only once. This line is an example of a tangent. It intersects it at exactly 1 point right here. This point is called the point of tangency. It's this point right here, where it intersects the circle. Next we have a common tangent. A common tangent is a line or a segment that's tangent to 2 circles at the same time. Now there are 2 different types of common tangents. There's internal and external. Common internal tangents intersect the segment that connects the centers of the 2 circles. So here are my centers with my segment that connects. internal tangent intersects this black segment. That would be an internal tangent. So for example, this line here is tangent to two circles, but it intersects at this point. It intersects that line. So this one would be an internal tangent. Another example of an internal tangent would be this line. Common external tangents do not intersect this black segment here. External tangents here are my centers. External tangents are just on the outside. They don't cross through the center there. They don't cross through this region. Next we have concentric circles. Concentric circles are circles that have the same center. So this circle P here and this bigger circle on the outside are concentric circles. They have the same center. Here's an example of two circles that do not have the same center. This circle has this larger circle has the center P, but the smaller circle has the center R. These two circles are not concentric. Next we have properties of tangents. So theorem 10.1 says if a line is tangent to a circle, so this line here, if it's tangent to this circle, then it's also perpendicular to the radius at the point of tangency. So if this line is tangent to the circle, then it's perpendicular to the radius. And this is my radius right here. And it's perpendicular at this point of tangency. Then if you're given a line, if a line is perpendicular to the radius at its endpoint on the circle, then the line is tangent. So for this theorem, if this line is perpendicular, if you're given that, if it's perpendicular to the radius, then you know that that line is tangent. These two theorems are this theorem is a converse of that theorem. Last, if two segments from the same exterior point are tangent to the circle, then they're congruent. So this segment and this segment are from the same exterior point and they're tangent to the circle, so that means that they are congruent, meaning this segment is congruent to this segment. So if this segment is 5, then this segment is also 5. Last, how to verify a tangent to a circle. Remembering that last theorem, if a line is tangent to a circle, so if this line is tangent, then it forms a 90-degree angle with the radius. The way to prove this would be to use the Pythagorean theorem, which would be a squared plus b squared equals c squared. So for example, we have 11 here, 60 is this length, and this length is 61. We need to check, is this segment really tangent or not? If it is, that means that this angle would have to be 90 degrees. So we need to check, is it 90? So to check, if a squared, so if 11 squared plus 60 squared is equal to 61 squared, if that's true, then that means this is a right triangle and this is a right angle, so it would be tangent. So let's plug our numbers in and see. So my a we'll say is 11 squared plus my b would be 60 squared. If that is equal to 61 squared, we don't know if it is though. If it is, that means that we have a right triangle. So let's see, what's 11 squared? That would be, what, 121 plus 60 squared is 3,600. Does that equal 61 squared? 3,721. Are these equal? Well, let's add these two. Combine these like terms. 121 plus 3,600. That equals 3,721. And yes, that is actually equal to 3,721. So because the Pythagorean theorem holds true, this is a right angle, meaning, yes, this segment is tangent to the circle. So you just need to verify using the converse of the Pythagorean theorem. And last, we are going to use properties of tangents. So we had a theorem that said if two lines were from the same external point and they were both tangent to the circle, then these two segments would be congruent. So our task here is to find x. So we would set up x squared plus 4. That should be equal to 13. So you subtract your 4 from both sides, and you're left with x squared equals 9. And you need to take the square root of both sides. And you have x equals the square root of 9. The square root of 9 is 3. But you could also have negative 3 for x. Because if you put negative 3 back in for x, let's actually do that. Negative 3, if we squared this and then added 4, we would get 13. So 9 plus 4 is 13. So you need actually both answers here for x, 3 and negative 3, because they both make this equation true. And that's all we have for section 10.1.